Good afternoon, everyone.
Good afternoon, sir.
Good
Good
afternoon.
afternoon, sir.
Good afternoon.
Afternoon, sir.
We'll start in a moment. So, we're going to take your doubts for the last 10 minutes or so. So, while I'm teaching, if you have a doubt, you could raise your hand by the Zoom button for raising hand, and then you could type your question in the chat. I will take those questions. I'll solve those questions starting at 4:50. Okay, and please do not annotate on the screen. ક્લાસમાં તો બોર્ડ પર આવું ગમતું નહોતું હે એમાં તો ટાંગા ધ્રુજતા હતા ને હવે અહીંયા તો વાંધો નથી આવતો ઓકે so in the previous lecture, that is yesterday we were discussing, we were trying to find out the electric field due to a shell. I would ask everyone to mute themselves. Okay, please mute yourselves. Okay, so we were talking about finding the electric field due to a charged shell, right? And we discussed that we could take a Gaussian surface around it so that it would pass through this point P. So we derived the electric field for outside case, and we got this answer here, right? This one, electric field outside is kq by r square. I was telling you that it's just like gravitational acceleration, which has a formula gm by r square, right? Okay, so what we are going to do is we will try to find the electric field inside it, right? Not just outside. We did it for outside yesterday. Now it's time for inside. So let's start. Again, I'm requesting all of you to mute yourselves. Okay. So suppose this is that uniformly charged shell. Okay, right? And we want to find out what's the electric field at some point which is inside this shell, right? We took one point outside earlier, now we'll take inside. So this is center C. Let's say we want to find the electric field at this point P. What's the electric field at that point P, right? As usual, the radius is R. Suppose the total charge on this sphere is Q, right? Okay, so what we'll do is we will draw Gaussian surface. Again, we will exploit, or we will use the spherical symmetry that we talked about yesterday, and we will draw a Gaussian surface like this, that is a sphere, right? So we draw a spherical Gaussian surface, right? So we will draw a spherical Gaussian surface, and suppose this point P is at a distance smaller, then all the calculations are same. The idea that electric field at every point on this Gaussian surface has same magnitude, all that is just a repeat. So I'll just start with this thing. Total flux for this Gaussian surface is equal to integration of E ds cos 0 as it was for outside, same for inside, right? Because there's no other change, right? So ultimately this will become E into integration ds. So that is E into S, right? That is E into 4 pi r square. All this is the same whether this Gaussian surface that we are taking is outside or inside. It doesn't matter, this calculation is going to be the same. Now by Gauss law, let's use the Gauss law for this Gaussian surface. Remember, this is the Gaussian surface here, right? So first thing, to use the Gauss law, obviously we need to write the formula. Sigma q enclosed divided by epsilon 0 is the flux. Now, how much charge is enclosed? That is, I'm asking you, what is sigma q enclosed? See, let's make it a bit interactive. Those who can hear me, right? I'm asking you a question. Look at this diagram. What do you think is sigma q enclosed, right? And type it in the chat box and give an answer, right? Don't worry about others' answers. Start giving your answers. Come on. What do you think is sigma q enclosed? Okay, we are starting to get some answer. Very good. Right. Okay, fine. So I think that is settled. It is settled that because there is no charge anywhere over here, right? This is empty, right? I hope you still remember I told you that this is empty part. So there is no charge. So it is settled that sigma q enclosed is 0. So if this is 0, then that means E into 4 pi r square is also 0 because flux is E into 4 pi r square. All right. So I think most of you have understood, right? So I'm quite happy about that. So E into 4 pi r square is 0. So that's why ultimately electric field is also 0. See, such a nice value, right? So what we have derived is that inside the shell, electric field is 0. So we can remember this as a formula. E inside for a shell is equal to 0. This is exactly what you have been taught earlier in gravitation chapter, if you remember, right? We had two sentences. One was that if you want to find out what's the the gravitational force inside a shell, then we were told that inside the shell the gravitational force is 0, and for outside you just have to assume that this whole mass is concentrated at the center, and then we used to do it just like gmm by r square, right, for outside. So same thing here. For inside, the electric field is 0, and for outside, you can just assume that all the charge Q is not on the surface, but rather concentrated at the center. So then you can just say KQ by small r square, just like a point charge, right? So this is behaving like a point charge. All right. So in in this way, the electric field and the gravitational force thing, they're quite similar. So whatever formula you remember from your 11th standard, you can use it here, right? And it will make very easy work of the whole thing. Okay. So with that, the textbook part, this theory is over. We still have to solve the last example. Omdeep, I request you to mute yourself. So we are going to solve the last example from the book. I think that is number 13. I don't remember the number, frankly, right? We'll have to see which number it was. If you have the book, open it, the last example. You can start reading it. Meanwhile, I will just copy that question over here. right? So we can start solving it. Okay, it is example 13, 1, 3. Okay, yes, all formula for gravitational force will work for electric field, right? Or electric force. Only that you just have to change G to K and all that. Okay, I've got the question. Someone is raising hand, but someone, your name is Redmi Note 9. I didn't know we have such names in India. Okay. Right now the question is on the screen. Hopefully all of you can read it. Some of you have raised hand again. Like I said, after you raise hand, put it in chat. Okay, I will read it. I will reply if it is worthy. Otherwise, we'll keep it for the end if required. Okay. So we have this question here. Let's start. An early model of an atom considered it to have a positively charged point nucleus of charge Ze. So what is given is that at the center of this, there is a nucleus. It's like a point charge, and its charge is Ze, plus Ze. Obviously, nucleus is positive. Mega, write down your question in the chat. And then it is surrounded by a uniform density of negative charge, right? So in this whole volume over here, as you are seeing in this picture, right, in this whole volume, there is negative charge. Now see, this is volume charge distribution. Volume charge distribution, that is, charge is on the entire volume, not just on the surface, not only here, but also inside, everywhere, right? So this is volume charge distribution, right? And its density is uniform, right? That is same everywhere. And its radius is r, given in the question. Okay. The atom as a whole is neutral, right? Atom as a whole is neutral. I think you all know that from your chemistry lessons, right? So what that means is there is point like plus Ze charge, and in this negative charge region, the total charge spreaded out of this negative region, total negative charge, is also minus Ze, right? See why minus Ze, plus Ze positive, minus Ze negative, so total charge is 0, right? So atom is neutral. That is what we have. Now the question is, for this model, I think you all know we can't see atoms, right? So people initially tried to make different kinds of model for atoms, Rutherford model, plum pudding model, right? Thomson's model, right? These models, I'm sure you have heard about them. So what is the electric field at a distance r from the nucleus? So it's a similar question, right? Like that theory. Okay, but we don't have shell, we have an atom. So the question is, if you take some point at a distance r, then what is the electric field at that distance? All right. Okay, so let's start. First of all, we will take a point that is outside. All right, we're going to take a point that is outside this atom. So let me just draw a simple diagram again. This is the atom. All right, here is nucleus. Okay, right, and there is all negative charge spread out here, and at the center there is positive charge. Suppose I want to find the electric field at this point P, which is outside. All right, so obviously the distance from the center is smaller, right? And see, this is once again, I think you have started to hate this word. There is spherical symmetry, right? Because atom is like a sphere, it's same from every side. So we will draw a spherical Gaussian surface. Okay, let me just draw it in another color so you would realize what we are doing. This is a spherical Gaussian surface. You see, I have not practiced drawing in lockdown, right? So this is the spherical Gaussian surface, right? And for that Gaussian surface, all the calculation that we did while deriving all that is going to be repeated. I don't want to do it again. E into 4 pi r square, right? Directly, this is the flux, right? and that should be equal to sigma q enclosed divided by epsilon 0, right? This is the Gauss law. All right. So now let's see how much charge is enclosed inside this Gaussian surface. Come on, answer that. How much is the charge enclosed inside this Gaussian surface? Remember, there is positive nucleus Ze and then there is minus Ze over here. Okay, I've already had some answers. Arshad, you can ask your question. Most of you are answering 0. That's correct, because plus Ze for nucleus and minus Ze for the rest of the negative, because atom as a whole is neutral, right? Okay, no charge, correct, Kodal, that's right, no charge. So total charge is 0. So that means the electric field, obviously I can divide this 4 pi r square on this side, right? Ultimately, I'm going to get E is equal to 0, right? So this is the electric field outside, right? Outside the atom, the electric field is 0. That is what is mentioned. Okay, but we still have to talk about inside, right? So let's start with that. I'm going on a new page here, right? That will be easy for us. So I'm going to draw a giant atom, right? So this is that large atom that we are talking about. Okay, and of course at the center there is nucleus, and now there is negative charge spreaded out uniformly everywhere in this atom. Okay, and now we want to take a point P, let's say over here, which is inside, right? So this time we are talking about inside. We finished calculation for outside. Now we are talking about inside. So for inside, again, same idea. There's spherical symmetry. We draw Gaussian surface, which is a sphere. So let me draw that. Okay, this is the Gaussian surface. All right. And this Gaussian surface, let's say its radius is r because P is at a distance r, right? So now we will use the same idea, right? Again, total flux is E into 4 pi r square, right? Because we did all that integration earlier, we don't want to repeat. Is equal to, okay, is equal to, again, Gauss law, sigma q enclosed divided by epsilon 0. Now, this is where it gets a bit tricky. Let me write the denominator first, and then we'll worry about numerator. So I want all of you to realize that inside this Gaussian surface, this is the Gaussian surface, of course there is a plus Ze charge here at the center, right? The nucleus, this is the nucleus. So that charge is definitely inside or enclosed. There's no doubt about it, right? But what about the negative charge? See, this portion which is trapped inside the Gaussian surface also has some negative charge, right? I'll repeat what I've said. This portion that I've shaded, that is trapped, right? It is enclosed inside the Gaussian surface. How much charge does that have? Come on, can you give me an answer? I'll give you a hint. This radius is capital R, right? And there is uniform charge density, right? So the question I'm asking you is, how much is this negative charge inside this region? How much is the negative charge inside this region? Is it minus Ze? I know it's tough to write all that. It's not minus Ze, right? Okay. Avinash, there is a simpler way. Well, let's see. I hope you got the idea that this is not going to be minus Z. It's less than that because there is some charge here as well, right? So how do we find it? Well, let's see. Look here. Charge inside Gaussian surface. Okay. Well, that is, okay, we are talking about negative charge inside Gaussian surface. unknown. But do you realize that in a volume 4 by 3 pi capital R cube, right, total volume, right, this is total volume of atom. In that volume there is charge minus Ze, correct, right? In total volume, this is total volume, right, the total charge minus Ze. Then in a volume 4 by 3 pi small r cube, right, the area, the volume enclosed by this Gaussian surface is only 4 by 3 pi small r cube, right? So in 4 by 3 pi small r cube, how much is the charge enclosed? That's what we want to find, right? So of course we will do it by cross multiplication. No, Vivek, your answer is not right. We will do it by cross multiplication. All right, Pranali, type your question. So that is going to be minus Ze into 4 by 3 pi small r cube divided by 4 by 3 pi capital R cube, right? So now what's cancelled? All right. So finally we have found out that the negative charge inside that Gaussian surface is minus Ze small r cube divided by capital R cube. So let's take this value and put it here. So this much is negative charge, so we should subtract. I think you understand why we are subtracting, right? Because that charge is a negative charge, so we subtract it. Again, how did I get this value? Have a look at this calculation. We say that in total volume, which is 4 by 3 pi capital R cube, the total charge is minus Z, right, for the whole atom, for the negative part actually. And then for Gaussian surface, the volume is 4 by 3 pi R cube. So what's the charge over there? We did a cross multiplication and we got this answer, right? That means here that much charge is subtracted because that charge is negative. Nucleus, this is nucleus charge, that's positive, and this is the remaining charge. So now if I want to find electric field, I'll have to continue my calculations from here. All right, so all this is done. Now if I want to find E, right, all I have to do is divide this 4 pi r square on that side. So finally I am going to get E is equal to Ze minus Ze small r cube divided by capital R cube, the whole divided by epsilon 0, and then also 4 pi r square that came in by division from the other side. So at the most I can take Ze common, okay, right, and yeah, that's it, right? So if I take Z common, I will get 1 minus small r cube by capital R cube, and then the whole thing is divided by 4 pi epsilon 0 r square, right? So this is how, this is what is the formula of electric field inside the atom, right? You don't have to remember it, this is just, you know, we solved the question, right? So this is the formula of electric field we get inside this atom, right? So with that done, this example is over, right? Now we are going over to the next thing that we are supposed to do from this chapter, and that is going to be question number 20. Question number 20 from the exercise. Okay. Right, I'm copying the question so that everyone can see it, even if you don't have the book. Okay. Someone's mic is still on. Can you please mute yourselves? Okay. So this is the question number 20 from the exercise. A point charge causes an electric flux of -1 into 10 raised to 3 Newton meter square per coulomb to pass through a spherical Gaussian surface. So suppose here is a point charge, right? Okay, and there is a spherical Gaussian surface of radius 10 centimeter. This is Gaussian surface, remember? This is the point charge, negative point charge. Let me just write minus sign over here. Okay, and that is centered on the charge done A. If the radius of the Gaussian surface were doubled, how much flux would pass through the surface, right? So in this case, because it's a negative charge, electric field lines will come towards the charge like this, right? So now the question is that instead of this Gaussian surface, if we take radius of Gaussian surface double, right? So instead of this Gaussian surface, let's call that number 1. Instead of that, we have another Gaussian surface over here, right? Let's call that Gaussian surface 2. So then for that Gaussian surface 2, how much is the flux, right? What do you think? Will it be more or less or equal? Okay, we are starting to have some early answers. That's right, it will be same, correct? Because the charge enclosed is same. Srishti, do you want to ask anything? If you want to ask something, can you please type that question? So the answer will be same because the charge enclosed is same, right? Some of you might have a question, why did I choose to solve? Well, some of you might have a question that if we increase the size, the radius of the Gaussian surface, should not flux also increase, right? But it doesn't work like that. It did not increase because this is a point charge, right? And for a point charge, the electric field is kq by r square. So if you double the radius, the distance of this Gaussian surface from here is also doubled. So instead of r, now it is 2r. So because of that, the electric field, which was earlier kq by r square, will now become kq by 4r square, right? Because the radius is now double, right? So although electric field is 4 times less, right, for second Gaussian surface, electric field is 4 times less. But look at its surface area. It is 4 pi 2r whole square. So what has happened is ultimately the surface area is also 4 times. So because of that 4 and this 4, the effect is cancelled and the flux remains the same, right? Actually, the flux does not even depend on the shape. I think I did mention that in the lecture. I frankly don't remember. Okay, but even if you would have drawn a square, the cuboidal Gaussian surface, it would still give the same answer, right? So the question is, what is the value of point charge? I think you can find that easily by using the Gauss Law formula. I'm not going to do it. Okay, so this part B I'm just leaving for homework. All right. Okay, so that is it. Right now, let's solve one more question, and that one is going to be question 25. It is one of the additional questions, but I think it is worth doing. So let's do that. Question 25. Okay. So let's start. An oil drop of 12 excess electrons. Excess means extra. See, generally all substances, they are neutral, right? Because they are made up of atoms. But here this oil drop, it has 12 extra electrons. So the charge of this oil drop is minus 12e. All right, because 12 electrons are extra. So that much extra charge is there on the drop. Now it is given that it is held stationary. So actually what it means is it will float under a constant electric field of 2.55 into 10 raised to 4 Newton per Coulomb. Okay, so this has some charge Q, right? Obviously it will also have a mass. So let's say it has a charge Q and a mass M, right? So because of gravity, it should fall down. Okay, we did this question earlier, really? Okay, fine. Some of you are saying that we have done it earlier, so there's no point repeating really. Okay, we'll stop doing it. Have we done 33? I'm asking you for 33. Have we done 33? Okay, fine, enough. Right, I got it. We have not done it. So let's do it. I think we solved it as a doubt, if I'm not wrong. Okay, never mind. We'll do 33. Okay, yes, Kea. I remember it now. Never mind, let's do it first. Okay. So this is where there is a particle of mass m, charge minus q, enters the region between two charged plates. Okay.
મમ્મી નહીં ના આંટી આવ્યા.
Please mute your mics, everyone. Vishwa, please do that. Okay, so suppose here is that plate. Here's another one, right? And this particle, which is having a charge minus q and mass m, is moving in the x-axis, right? So this is the x-axis, and length of this plate is L, and uniform electric field is maintained between the plates. So suppose the electric field is downwards, right? So because of that electric field, right, due to electric field charge minus q, negative charge, will experience force. In which direction? Answer that one, everyone, hurry up. In which direction? If the electric field is downwards, the charge will experience force in which direction? Okay, because it is a negative charge, right? Correct, because of the negative charge. So the magnitude of the force will be modulus, or rather only q into e, right? Okay, so its acceleration can be found, but this force is in y direction, right? Because electric field is vertical. So if you want to draw an FBD of that body, then there will be a force like this in y direction, and that force is nothing but QE, right? We are going to ignore gravity here because I think you know that gravitational force is very weak compared to electrostatic force, right? Okay, so we will not write mg. Okay, so this is Fy. In x direction, there is no force because electric field we have taken it to be vertical, right? So now this particle will start going upward slightly because there is an upward force. It will go like this. It will not go in a straight line, right? Okay, in fact, it will be like a parabola, but that's not the point really. So it will go upward. So if you watch it from the side, instead of going straight like this, it's going up. So we have to find this vertical deflection. I think we should call that vertical displacement delta y, right? So if we know ay, we can find it easily from this. Ay is equal to QE by m. Okay, right? So most of you have got it correct that the deflection is upwards or the force is upwards. So this will go up by distance delta y, right? So our aim is to find delta y. And you can see here that acceleration is constant because charge, electric field, and mass all are constant, right? So this is a constant. So we can use equations of kinematics. But there's only one problem. We don't know time. That is, in how much time it will go from this point A to this end of the plate B, right? Okay. So for that, we will take x-axis. You see, on x-axis, the particle moves from this to this point, right? So that means delta x is equal to L. All right. So if delta x is equal to L, from that and from this that we have ax is equal to 0, right? Fx is 0, so no acceleration, right? So constant velocity, so I can write L is equal to velocity x direction, x component, into time t, right? Because there is no acceleration. Acceleration is 0, right? So from this we can find time. So it will take how much time to cross? This is the time to cross the plates. All right, that is to go from between the plates, right? So in this time L upon Vx, this particle will move from A to B, right? It will take that much time, L by Vx. So finally, if you want to find how much is the vertical displacement, let's use equation of kinematics, right? Delta y is equal to V0yt plus half AY t square. I think I don't have to remind anyone about this one. So let's put values. Initial value of y component velocity is 0, right? Because it is given that it is moving along x-axis, right? It's mentioned in the question. Plus half, instead of AY, where did AY go? Over here. AY is QE by m into t square. T square is L square upon Vx square, right? So based on this, we have got the answer. So that is it, right? And if you have understood, I think you should try question 34 on your own as homework, because that's just a question with some values given. All right, it's practically the same as this 33, right? Okay, and you just have some values, so you just have to put it, do some calculation, right? Okay, now let's solve question 26. That will be the last question for today, and then I'll take your doubts if you have any. All right, question 26 from additional exercises. How do we know it traveled? It wasn't that possible that yes, yes, you are right. It is also possible that if the field is very strong, it will hit, right? But I think the question does mention, see, given that show that vertical deflection of the particle at far edge, that is when it reaches over there, it has this much vertical deflection, it is given, right? But yes, you can also find a condition that for this much electric field it will hit, right? And if it's less than this, it will not hit. All right. Okay, Rutva, I hope that is clear. So we have practically assumed that it doesn't hit, right? Okay, let's solve 26 now. Please give me a moment. I'm copying the question. Okay, let's start. So you see, this question is about properties of electric field lines, right? Okay, so we have talked about many properties. I think I did a lot of, I noted down a few points, right? So if you have those points written down, it's very good. It will help you to solve this question. Suppose you remember those points, it's actually even better, right? Because you are actually required to remember those points. So here, Sakshi, why don't you type your question out if you have it, right? So we have to worry about the properties of electric field lines. All right, that's what we are going to do, right? Okay, properties of electric field lines. This is A here. A is about a conductor. Actually, this is best solved after we study second chapter, this particular A, right? So leave this at the moment. Don't worry, it's not tough. Just that whatever is required, we will study that in the second chapter. Okay, right? So we will start with, do not just raise your hand, type your question. So we will start with B, right? So have a look at B. Is something wrong with B? What do you think, people? Yes or no? Is something wrong with B? Yes or no? Okay. So many of you are saying yes. All right. Okay. Mm-hmm. Okay. Uh, I wish there was some, shortcut here by which I could just click the name of a person and unmute that person. Okay, so many of you have given reasons, right? There are more reasons if you can think of, but the basic reason is here field lines over here at this point, they are going into into positive charge, right? The field lines are going into positive charge. That's obviously not possible. So this is what is wrong. All right. So that's the reason B does not represent it correctly. Okay. So now we go to C. This is what we are talking about now. Come on. Is C okay, or do you see something wrong with C? Okay. So you are saying that C is correct. That's fine actually. Right here, the field lines are curving like this because there is a positive charge. So what happens is, because of two positive charges, the field lines that were supposed to go like this instead, right, will start curving out in this manner. All right. So B is correct. There is nothing wrong with B. Well done, people. Now you have D. D is obviously rubbish. Tell me why it's wrong. What about D? Is it right or wrong? If wrong, why is it wrong? Why is it incorrect? Okay, very good. Field lines cannot intersect. Very well identified, people. Right here you can see the field lines are intersecting. That is not allowed, right? That's not how it happens. So intersecting is not possible. So D is wrong. Okay. Now fine. Okay, now let's go to E. Let's go to E. What do you think about E? Is it correct or not? Okay. Cannot form closed loops. So actually, if you look at it carefully, there are two mistakes or two things that are wrong. One is that closed loops are formed, right, over here. And the second thing is that you see these lines, they have not shown what's next, right? These are okay because you cannot draw till infinity, right? All the paper in the world will not allow you to draw all the lines. So that's not a problem, but this is a problem. Here they have terminated it. This is stopped. That's not how it works, right? It should not stop. Okay, so that's why there are two mistakes. One is can't be a closed loop, right? And the second is cannot stop like this abruptly over here. All right. Okay, so that's why, because of such reasons, this is also wrong. Charge is traveling from positive. No, Swarali, charge is not traveling. This is not charge, right? These are field lines. These are not charge. Nothing is traveling. Remember everyone, field lines are actually imaginary, right? Okay, this is like equator on Earth, right? Equator that we have drawn, right? There's no equator actually on the Earth. So that's it. Now, is there any more? No, I think we are done. A, B, C, D, E. Fine. So we will stop for today's content. Do you have doubts with anything that I've taught you today? If you have doubts, write it down in the chat immediately. Okay, I see people are leaving. Goodbye, people. Nobody has a doubt? Okay, so because nobody is asking something, I think we have a few minutes. We could use those, right? Okay. So I'm giving you one question to practice, right? Have you thought of infinite cylinder electric field? No, it's not given in your textbook. Why should I teach it? Right here. If it was not uniform in question 33. Okay. Right? Okay, the 33 is the one with plates, right? So let's go back to that. This one. So here, if it was not uniform, then you really can't predict what will happen, right? So in that case, this will move. This might move in a weird manner, right? So you need to know how exactly electric field varies or changes with place, right? So it is important that you have been given some kind of relation. Otherwise, you can't really predict. All right. So then it would not be a parabola. It might be some weird shape, right? Okay. Um, okay, we have one more question. If positive point charge is brought near metal shell, then it will get charged uniformly or not. Okay, right? So suppose this is a neutral shell or sphere, right? Okay, and here we bring a point charge close to it. Okay, then the question is, will it get charged uniformly or not? See, fact is that this is a neutral shell, means its total charge is 0. So because of this positive, it's going to attract electrons from the whole shell, and the negative charge will come close to this. So because of that, and the rest of the things, that is, if electron leaves an atom, I think you know that it will make ion, right? So those ions are positive ions, right? Those ions are positive ions. So those positive ions are actually going to be repelled. So what will happen is, ultimately, when there will be equilibrium, these positive charges will settle on the outer surface on this side, right? So this is not uniform. This is not uniform because there is negative charge on the left side but positive charge on the right side, so it cannot be uniform, right? But if point charge was not over there, it was over here at the center. Suppose this point charge is at the center, then all the negative charge will settle on the inner surface, and that will be uniform, and the positive charge will settle on the outer surface, right? So in that case, this will be uniform, right? Because there is again spherical symmetry, right? Okay, I hope, Srusti, I've answered your question. Okay, any more questions, people? Okay, I think we would stop. All right. Okay, I'm ending this meeting. Goodbye, everyone.